Guys, this is Mr. Gagnon again. We're into the end of the section here on dynamics, and this is generally the hardest for students to understand. We're looking at tension and apparent weight. So this is from number 67. It looks like 67 to 74. Okay. 67 to 74. So first of all, we've got to know what tension is, and I'll give you just a brief description of tension. Let's say I have a string. Here's a string. I got a mass hanging from the string, and this is attached to like the roof or something. Now, the tension in this string is equivalent to whatever the weight is here. So let's say we got a 2 kilogram object. Weight is mass times gravity. Okay, what kind of tension do you have? Well, the tension is going up. Weight is going down, so tension is the opposite of weight in this situation. So it's 19.6 newtons. Okay, so that's the tension in this string or this rope. Now, things get a little more difficult when we have, let's say I were to take this and start moving it. Because now you've got something happening where you're changing the apparent weight of this object. Okay, and I'll just give you guys an example of a situation where the tension in this string would actually disappear. Okay, so let's say we had a situation here. Same deal. Mass hanging from a string. Okay, weight's pulling down. Okay, the situation where this tension would be 0, okay, would be a situation where this object accelerated downward. In other words, you get into a free fall, and this object now becomes apparently weightless. No tension in the string. Okay? So we're going to take a peek at a few of these problems. Okay, what I'm going to do is take a peek at number 67 to start, and let's see if we have enough space for it. So I'll start with number 67. Okay, so in 67 it says a 1,500 kilogram elevator. Okay, so mass of the elevator is 1,500 kilograms. It moves up and down on a cable. It says calculate the tension in the cable for the following cases. Okay, in the first case, it says that the elevator, in case A, moves at a constant speed upward. Okay, so here's, well, we can use the same picture because elevators are attached to a cable. Let's say I had a pulley. Here's the elevator. That thing is going at a constant velocity upward. Okay, that means it's constant. It's not accelerating. It's just moving constantly. In this case, okay, the weight is equivalent to the mass times gravity. So if we figure out what the mass times the gravity is, okay, the weight is 14,700 newtons. Okay. Now, in a non-accelerating object, now if you were in this elevator and it was moving constantly, you wouldn't feel it. Okay, when I say you wouldn't feel it, you wouldn't feel any queasiness in your stomach. You wouldn't feel any acceleration there. So the weight of the object is equivalent to the tension going in the opposite direction. So tension in this case is 14,700 newtons. Now, part B, it says the elevator moves downward at a constant speed. Okay, now again, there's no acceleration in there. You're in the elevator, you're not feeling any difference in your apparent weight. So the tension stays the same in part B. So part A and part B, very easy. The tension equals the magnitude of the tension pulling up equals the weight pulling down. It's almost like the normal force. Now, part C says that the elevator, let's see, draw the elevator again, is accelerating upward. That means the velocity is changing upward. Okay, so now we've got a situation where we have a tension pulling up, okay, that is increased. So let's take a peek at it. Okay, weight is 14,700 newtons. Okay, we know that weight is mass times gravity. Now, we've got our acceleration of gravity here, but it's pulling up. So imagine you're in the elevator. You're in the elevator here. If something's pulling you up like this, it's going to feel like while you're accelerating that you weigh more. Okay, just get that image in your mind that you'll actually feel like you'll weigh more if we're accelerating upward. So the tension in this situation has to be greater than the weight. Okay, we know that. Okay, because the tension is the force in this rope cable. Now, knowing that the tension is greater than the weight, we know that it's going to be at least the weight plus the mass of this times the acceleration of this in the direction. Okay, so we've got a little formula here that gives us tension is weight with the weight times mass, weight plus mass times acceleration. So the tension in this cable will be 14,700 newtons plus the mass of the object, which is 1,500 kilograms, times our acceleration. And they told us in part C that the acceleration was going upward at 1.2, I can't fit the unit there, meters per second squared. So let's take this T down here. So tension in there is 14,700 plus tension is 16,500 newtons. Okay, that's the tension in that rope as it's pulling up. So realize that if you're accelerating up, it's increasing the apparent weight of that elevator and causing more tension. Say 16,500 newtons worth. Okay? Now, part C is done, but now we got to figure out what part D would give us. So we have this, we're still in 67. Okay, we're finding for tension. Okay, solving for tension. We have our elevator here. Okay, the elevator now is accelerating down. Okay, so if tension equals weight plus mass times acceleration. Tension equals, and one thing that I did not mention to you guys was that we're actually using the absolute value of the weight. So tension, because weight is the opposite of tension, so we're using since weight's negative, we're using the absolute value. So tension is the weight, 14,700 newtons, plus the mass, 1,500 kg, times, now this 1.2 was up, so it's positive. The 1.2 is down in this situation. So tension, 14,700, there's a negative sign here. So 1,500 times 1.2 minus 1,800. Tension in the rope is 14,700 minus 1,800. 12,900 newtons. Okay, that's with it accelerating downward. Now, if we approach 9.8 here, just to give you a situation, if we approach 9.8 here, this tension drops down to 0, okay, as we approach 9.8. Okay? And then if we go further than 9.8, you get a situation where you start to levitate. So we'll talk about a couple of those as well. Thank you. Have a great day.